Hello, everyone. My name is Jiankang Deng from Imperial College. Today I will present my research work on face recognition. The title is Rethinking the Face Recognition Paradigm with a focus on accuracy, efficiency, and security. Here is the outline of today's talk. I will first start from the background of deep face recognition and introduce my past research work, such as ArcFace, and then give us short summarization for deep face recognition. And after that, I will introduce two VIT-based face recognition method named TransFace and TransFace Plus Plus. And finally, I will give some introduction about my future work. So face recognition systems are widely used across personal, commercial, and government domains. So such as phone locking, unlocking, airport security, boarding, and surveillance camera, and doorbells. So the timeline of face recognition evolution tracing the transition from handcraft features to deep learning-based approaches. About 50 years ago, the initial version of face recognition is only based on some distance template. And at the beginning of 1990, and there is two famous methods. One is named Eigenface, and another one is named Fisher face. But both of them are operate on the pixel space, and it's not robust for the under facial expression variation and the illumination variation. And after that, the community started using some handcraft features like Villa Jones, HAR feature, and LBP feature, SIFT feature, until recently, when deep learning becomes mainstream in the community, and the face recognition community also benefit from the development of deep learning, and all the face recognition model nowadays are based on deep learning. At the beginning, 10 years ago, the face recognition is mainly focused on the method like classification-based, metric learning-based, deep face, and FaceNet. And recently, when I started my PhD, the research focused on the margin-based softmax loss. And here I give a figure about the number of face recognition publications over time. As we can see, the publication number steadily increase at the early 2010s and 2010s, and then follows an explosive increase with the rise of deep learning, and peaked in the year of 2022. And then recent 3 years, there is a slight cooling off of the research in face recognition. And for the early approach of face recognition, let me first introduce one classical method, Eigenface. This paper is published in 1991, and the method is very simple. It's the author collect a group of face images and calculate the average mean face, and then they calculate the eigenvector of the covariance matrix of the normalized face. And or for any input faces, it can be represented by a weighted sum between the mean face and a group of eigenfaces. And the eigenface is a generative model. It can reconstruct the faces and can also work for the face imprinting. And the parameters here for the eigenvectors can be used for identification. Eigenface is proposed more than 30 years ago, but I think it is still insightful for the research. Until recently, we also consider how to inspired by the principal component to for the image generation in this year ICCV. So Eigenface is based on, as I said, Eigenface is based on the pixel space, and it is not robust for real-world variations. Recently, we moved forward to the deep face recognition. And the main challenges of deep face recognition is there is high intra-class variations, such as age, pose, and occlusion. And there is also interclass disturbance. And in this world, we have almost 8 billion identities, and there is also some technology that can do some impersonation. So the target is also very clear for deep face recognition. We need to achieve very good intra-class compactness and inter-class discrepancy. 10 years ago, when I started my PhD, there are two main trends for deep face recognition. One is from VGG group. They are following the classification framework. Given a large-scale dataset and a deep neural network, what they are doing is they project the embedding vector through a FEC layer to classify the similarity. Similarity is also called the logit. And then this logit is compared with the, is normalized by the softmax function to get the normalized probability. And then compared with the one hot vector, this is the ground truth. And the loss is the cross entropy loss. So the classification framework can achieve separable features, but it's not discriminative enough. And at the same time, researchers from Google, they employ Google Net, and they designed a famous loss named triple loss. What they are doing here is they remove the FC layer. They design a loss that the negative pair, the distance between negative pair need to be far by a margin than compared to the positive pair. So, but this method has some training difficulties because we need to construct effective triplet from large-scale training data. So when I start my PhD, I'm considering we need from those two methods, we know that classification loss is easy to train, but the feature is not separable. And for triple loss, the margin is important, but it's not easy to train. Why not combine them together? And this is the motivation of my ArcFace work. So what we do here is we have an embedding vector from the network, deep neural network, and then we have a FC layer, and we normalize those two representation and multiply them together to get the logit. And then for the target logit, we calculate the angle between the feature vector and its center, corresponding center, and we add a constant margin, angular margin here. This margin is the arc is around arc value is around 0.5 and it's around 25 degree, and then we calculate the cosine value again and put those logit to the this target logit to the logit vector. And because we have feature normalization here, we need to scale back the number and scale back the logit. And then the following step is similar to the softmax loss. By introducing the additive angular margin, we can see here our representation embedding are more compact, and the design boundary are more clear. Yeah. And so for to train ArcFace more efficiently, we implement a method that not only have the parallel acceleration on the features, but also on the FC layer. And for each graphic card, we first calculate the feature embedding, and then we aggregate those features. And the Fourier connection layer is divided to different graphic card, and the forward path is feature x times the submatrix of W. And then for the backpropagation, we know that the gradient for coarse entropy loss is target logit -1. So it is very easy to calculate by hand. And then we can calculate the gradient on the submatrix of centers and the gradient of the feature. And in this way, we can easily handle 1 billion identities within a graphic card, on the graphic card with the memory size of 12 gigabyte. And this is the main limitation when I started my PhD. I remember by then we are using the Titan XP, and the memory size is around 12 gigabyte. And as we can see that when we divide the four-layer connection layer to different graphic card, and when we have more identities in the training speed is decreased only slowly, not as a naive implementation of the softmax loss. ArcFace achieves very good performance, and in the disguised face recognition challenge, we achieved the first place, and our predicted similarity is more reasonable than the other commercial API. Here we give an example of Albert Einstein, and the impersonation here shows less lower similarity compared to the real pair. Here we show a video example, and given those face crops, we run face detector on each frame. There is no temporal smooth. As we can see here, our ArcFace feature is very robust under pulse variation or even occlusion. So ArcFace has a good capability for discriminative feature embedding. Here we also consider similar to eigenface whether ArcFace is generative. Here we design an experiment for ArcFace inversion. Given a random noise at the same size of the face patch, we get assign a label here. It can be a feature vector or identity label. Yeah. So in the forward pass, we can get a loss whether this input is similar to the assigned label. And then we can backpropagate this gap to the input, and gradually we can restore this image. So this is called ArcFace inversion from the embedding vector to the original face images. So what we are doing here is quite similar to eigenface, that we explore the mean and the variance stored in the batch normalization layer, and we ensure during the inversion process, the statistics of mean and variance follow the phase prior stored in the batch normalization layer. As we can see from here, when we employ the statistics from batch normalization, we can easily reconstruct the face images from the discriminative network. Here, we do not have any adverse learning, so the result may include some artifact. But as we can see from those results, the network can reconstruct the identities. And in the middle row, this is the result without using the BN statistics. As we can see, when we use the batch normalization statistics, the result is much better. And the inversion can be applied to different groups like young, old, or different races, different poses, and even under occlusion. However, because ArcFace is not trained with the explicit attribute constraint, so there is some general confusion. For example, the last row we show that after the inversion, uh, the gender can be confused. Yeah. So because the identity can be decoded, and this empowered a lot of applications, such as the identity decoding for the geometry. This is the ECCV work from MPI, and for ourselves, we also have some follow-up works from identity to texture, identity to albedo, identity to reflectance, and this is all of those research work are based on the identity coding. So since we have a very good discriminative learning framework, we are considering whether the training data can be also scaled up. Before we propose this web-based dataset, the largest public available dataset is only 85, contains 85,000 identities. And we are considering to enlarge this dataset by 10 times. And what we are doing here is iterative self-training procedure. So what we are doing is we collect a large-scale name list from the internet. We combine the IMDb and Microsoft 1 million data list. There are around 5 million identities. And then we download those images from internet and put the images from the same name into the same folder, and we conduct the intra-class and the inter-class cleaning. And the cleaning, all of the cleaning is in automatic way. So the first round is we have a model trained on Microsoft 1 million. We conduct intra-class cleaning and to select the dominant class from the folder, and then we calculate the average embedding for this folder, and then we run the inter-class cleaning. And after we get one version of the cleaned dataset, we retrain the network, and then we use this retrained network to clean the dataset from scratch again. And after several rounds of iteration, as we can find here, the inter-class confusion disappeared. So, and through this automatic way, we build a very large-scale, high-quality training data for face recognition. Here we give some example, and from the original example, we can see that the folder contains some unrelated faces. For example, those celebrities have their friends, have their connections, and all those images are downloaded into the same folder. And then our automatic cleaning method can gradually remove those intra-class noise and achieve very good performance after several rounds of iteration. Here we also verify our automatic cleaning strategy on the Microsoft 1 million dataset. And for the intra-class clustering, we compared with different methods, but the conclusion is we do not need very complex method like GCN-based method. We only need to use a very simple clustering method, and like a DB scan, we can get a very good intra-class clustering. And here we show the statistics of web-face, and web-face contains diversity in age, nationality, profession, pose, and races. Here we list the detailed identity decrease during our 3 rounds of iteration, cleaning iteration. And after we obtain this large-scale dataset, we verify our net training on this dataset. And as we can see here, as we increase the GPU number, we can almost achieve achieve linear acceleration of training, and the performance is not affected by the large batch size. And here we also show the comparison between our web-based dataset and the existing dataset. The performance of our dataset envelop the other competitors. Here we show some detailed information regarding the acceleration, and we also did a comprehensive comparison between different laws and on different datasets. Our web-based dataset is very competitive on those benchmarks. Here we also compare, we also benchmarking our method across different networks complexity, and here we show that for small network structure, some specific designs such as RegNet can achieve better performance than RedNet. But for large-scale dataset like RedNet 100, RedNet 200, change the network structure do not affect too much about the performance. RedNet itself can achieve very good performance already. So after we have a good learning method, ArcFace, and a large-scale training data, we reconsider the limitation of margin-based softmax loss. So here we list three limitations. The first one is because our large-scale training data is constructed automatically, and there is inter-class conflict within this dataset. That means some face image that belong to multiple classes, because we cannot ensure there is zero inter-class conflict. When this happens, there will be gradient confusion. And another thing is web face is collected without any balance. So the distribution of this dataset contains some tail classes, and those tail classes can undergo too many passive updates. So this is the second limitation. The third limitation is when we have more classes, for example, 10 million, we can divide the Foley connection layer to different graphic card, but in the Foley connection layer, when we calculate feature times center W, there is a logic. The result of this calculation Foley connection layer, their size is also very large. So in order to solve these three problems, we are considered to further improve the margin-based softmax loss. Here, we show that this is the basic formulation of the loss of softmax, and the gradient on the embedding feature is a weighted sum of centers in all of the centers. Here we use the P plus to indicate the similarity between X and its corresponding ground truth centers. And if this similarity is low, there is more penalty. If this similarity is high, there is almost no penalty. And for the gradient on the class center, it is also a weighted sum, but it's from the features, from the batch size. Here, eta is the learning rate. To solve these three problems, we propose the partial FC. Partial FC is very simple. What we are consider here is we keep the positive class center, but we randomly select the negative center. For all of those centers, they are saved in the memory, but only the active negative centers are copied to the GPU for the calculation. As we can see from here, we can not only save the space of the centers, but also save the space of the logit, because the logit is the dimension of the logit is the batch size times the class number. So the size of the logit use a lot of memories from the GPU. After we employ the partial FC, we can see here the similarity between feature and the center still can reach a very high status. But for the similarity between the centers, the similarity increase. This is because the optimization between the centers, the frequency of optimization decrease, so the similarity increase. But we can see from here, even under very low sampling ratio, for example, we only sample batch size level classes, and we can still achieve very good performance compared to contrast loss. What the main difference here is we maintain the centers for each class, and contrast loss do not have such kind of center. And we believe that the global moving average provides some very stable information for optimization. As we can see from here, after we apply sampling ratio of 0.3, we can significantly save the GPU memory and decrease the computation latency. Yeah. Here we show that the partial FC combined with arc-phase loss can achieve very good performance across different benchmarks. In the NIST evaluation, our result achieves ranks 15 by then when we propose this method. So let's give a short summarization about my former research on face recognition. And for the better lessons for face recognition is we also found similar things like what Sutton said. The great power of general purpose method when scaled with increased computation and data, we can achieve very good performance. What we have to do here is still using a very simple classification framework, and we scale up the training data. We also make the training very efficient on large scale dataset, and we achieve a very good performance. And for face recognition, let's reconsider the three component dataset. For the dataset, network, and the loss. For the dataset part, we try to increase the size of the dataset and achieve very good performance. And here we show the performance improve when we increase the image dataset size, the image number, and also increase the number of subjects. What we also did some choose some design for the input. And for FaceNet, it's a large crop, and for VG face, the crop is smaller. And for arc face, we choose a very tight crop, and the resolution is also decreased. We use a very small crop compared to FaceNet and VG face. And for the network design, for the same-based structure, we didn't change too much about the network structure. We just removed the downsampling step because our input is smaller. And here we also mentioned about the transformer part, but I will give a more detailed introduction regarding the transformer part. And for the loss, we know that the triple loss proposes the concept of a margin, and we make this margin-based classification more feasible by pushing the feature and the center to the sphere and introduce the margin in this sphere space, and this works. And as we can see from the performance on the various benchmark, and as we can see from here, for post-invariant face recognition, CFP-FP, IGBC, the performance almost saturated nowadays. And for tiny face, IJBS, because the quality of the face image are very low, there is still space we can improve. And the examples we believe challenge 18 years ago now is no longer a challenge, and we can handle very very challenging face verification tasks nowadays. And for those cases that face appearance is almost invisible, it is still a challenge case for us. Besides the academic benchmark, I also give the result on the NIST verification. NIST is industry level face recognition benchmark. It contains around 12 million identities. And here we choose the web face dataset trained with the RedNet 200, face loss plus PatchFC can achieve very good performance here. And here the force match rate is 1 from 1 million. And we can see from all of those results under different scenario like visa to visa, mugshot to mugshot, visa to border, border to border. And all of the recall, TR, true acceptance rate, can be over 99%. Okay, so those are our research work a little bit early, and what we are doing recently is moving forward to the transformer-based face recognition. Vision Transformer has demonstrated powerful representation abilities in various visual tasks. But the performance of VITs is almost equal, or they didn't show obvious advantage compared to CNN. So why? Is it because VIT lacks inductive bias, or VIT is easy for overfitting, and it is a data hungry method? So to answer those questions, we designed the VIT-based face recognition, and the structure here is includes the basic transformer framework, and we introduced dominant patch augmentation method, and we also introduced hard negative mining method here. And to alleviate the overfitting phenomena of VIT and improve the accuracy of face recognition model, we first think about the instance level data augmentation. But those instance level data augmentation cannot keep the structure information of face structure. So it is not very suitable for the face recognition task. Since VIT are prone to overfitting to some certain local regions, for example, the pre-trained VIT model sometimes focus on the face, like the eye region, to make the decision. So we are considering whether we can have a patch level data augmentation. Those methods need to preserve the key information of face and also increase the sample diversity. What we are doing here is, first we have a SE module that can select the dominant patches from during training. And to relieve the VIT from overfitting to those dominant patches, a natural idea is to let those models to see more diverse patches. Here we employ a linear mixing mechanism to randomly perturb the amplitude information of those dominant patches. So those patches go through the FFT and to get the phase and amplitude spectrum, and then we design a linear mix. We linearly mix the amplitude spectrum of those dominant patch, and then we combine those mixed amplitude with the original phase, and then we do the inverse FFT. So what we achieve here is we have a patch level augmentation, and this works very well for VIT-based face recognition. And as we can see from those examples, those dominant patches are mainly distributed near eye regions, and the proposed patch-based augmentation can efficiently relieve the model from overfitting to those dominant patches and encourage VIT to utilize those remain face cues to assist the final prediction. So another improvement is related to the hard sample mining, and for CN-based method, the hard sample mining is usually based on instance and based on the prediction probability and loss. And the global tokens of VIT may be dominated by a few local tokens. So we are considering entropy-guided hard sample mining, which can combine local and global information and mine information contained in each patch. So the detailed steps are listed here. We first estimate the local information entropy, and then we aggregate those entropy and use entropy-aware weighted mechanism to reweight samples. And we combine this hard sample mining with the formal arc-phase loss. So here we should realize some phase information entropy, and we can see that for easy example, those clear examples, they usually contain richer information, and for those low quality examples, they usually contain less information. Here we show the result of train phase. We can achieve very good performance across different benchmarks, across different model size. Yeah. Let's skip the analysis of the result. And then let's move forward to the next part about transphase plus. What we are considering here is how we can design a more safe face recognition pipeline and the VIT and apply VIT on the image bytes. So currently the face recognition is based on the decoded RGB image, and there is potential of privacy leakage. But if we design, whether we can design a face recognition model directly on the image bytes, and if we combine this image bytes with some privacy preserving hardware, we can make a very safe face recognition pipeline. So what we are doing here, this transformer block is similar as before. What we are adding here is some structure prior. We designed two modules. One is TIBC to extract a compressive bytes feature, and the SICA module establishes the interaction between bytes tokens and structure information through cross-attention operation. Before I introduce our method, let's first give a short introduction about the persistent homology, which is designed to uncover the intrinsic geometric and topological feature of the data. The concept is a little bit not easy to understand, but if I give an example, it will be easy to understand. Here we have a simple signal, and when we increase the threshold, and we can get a persistence diagram. And for this specific point, here, the birth and death is saved here. And if this point is close to the 45 degree, that means it's the time for birth and death are very close. So if we remove this point, for example, remove these 2 points, the main structure of this signal doesn't change too much. And if we increase the data size, like 1,000 points here, and we can see that if we keep 255 persistence value, the signals can still recover. And here we show how the signal changes when we remove the persistence value from the 45-degree line. So as we can see, when we decrease the value, the signal can almost, the structure of the signal can still keep, but there are some noise information or high frequency information are removed. So for our image byte-based face recognition, we apply the similar method, and we apply those we apply the persistence. We apply this TIBC module, and for the image byte-based compression. Yeah. Here we have a byte projector that can project the image bytes to embedding into the embedding, and then we add the TIBC branch, and we keep the structure of the original signal and maintain the main information in the signals. And for this part is for the input, and then for the during training, we propose a novel structure information guided across attention. Here we view every hidden point as every hidden feature as a high dimension point, and use VR complex, and we get the PD, and then we vectorize the PD to PI and inject this persistent homology into the cross attention module. So here is the quantitative result, and we can see that when we include our module to the later stage of the network, we can achieve very good performance and boost the structure preserving prior at the beginning, at the end, can improve the performance here. Here we show the result of our method across different benchmarks and different network structures. At the end of this talk, I will give a short introduction of our future work. Now, the face recognition is based on face only, and in the future, we are considering whether we can have interactive reasoning biometrics that can take advantage of multimodal informations and make the correct reasoning and predictions. So from face to general object, we also use this classification framework in our feature representation learning, and it also works very well. And another thing is regarding the personalized image generation. In ArcFace, we released everything in the inside face, and we have a face swapping module. And this face swapping module is used by almost 1 million servers in Discord, and it can easily generate face images of any person in this world. And this raises a following concern about deepfakes. So one of the future research work I will focus on is how to design generalizable deepfake detection. And this deepfake detection needs to be generalized across different GAN and different models, and work on multimodal audio and visual content. Yeah, those are the reference of the research work I included in this presentation. And all of our training data, training code are included in the GitHub of Inside Face. Thanks, everyone.
Thanks to the great presentation by Dr. We now have 3 minutes for questions, maybe 2 questions.
Thank you, Jiankang, for your presentation. Okay, thank you. I have one question. You just presented, how to make the VIT works well for facial recognition because for a very, very long time,
Yes.
VIT couldn't beat the CNN for facial recognition specifically. You presented two solutions. One is about the data computation.
Yeah.
Another one is about the hard sample mining.
Yes.
I think those strategies can also be used for CNN.
Yes.
And why do you think it's specifically suitable for VIT? And
what we do here is more related to patch-based. It's not instance-based. For example, for data augmentation, we are not instance-level data augmentation. We are patch-based data augmentation because VIT is prone to overfit to some specific patches on the face. We proposed a method to use the amplitude immersion to increase the diversity of this dominant patch. And thus the VIT is not easy to overfit to this dominant patch. And then for the hard negative mining, it is also based on the patch immersion, the patch immersion, not the whole face image immersion. It's patch-based instead of instance-based. So all of those two designs are more customized to the VIT design. Yeah, this is the main difference.
Okay, for these two factors, which one do you think is more important for VIT performance?
The first one.
Data augmentation.
Augmentation is important.
Okay, thank you.
Yeah.
Yeah, maybe one more question.
Thank you for the very interesting talk. One question about the persistent homology that you use.
Yes.
So, how is homology encoded? Is it just by edges, so you just need a distance, or it's by a complex, like you have also faces, tetrahedra, and so on, in higher dimensions?
Yes. So we have two kind of structure information used in our transformer. First is the byte length is the length of the byte sequence is very long. So the first application of PD is we apply to the original bytes information sequence, and we filter some noisy information and keep the main structure of this data because not like the 2D face image, we have the clear facial structure. And if we train from the long bytes sequence, there's no such kind of structure information. So the first application is we treat those signal as a 1D signal, and then we remove the less important persistent value that is around 45 degrees. And in this way, we can compress the signal or original signal. And then another one is in the end of this network, we have the patch-based tokens. And we view each token as a high-dimensional points, and then we construct the VR complex. And then we build the PD persistent diagram and project this PD persistent diagram into a PI vector. And we use this vector to into the cross attention. And this vector records the structure information of the face. So this is the main application of this PD information. Yeah.
Okay. So yeah, thanks to Dr. Deng again. We will have the first accepted presentation part. So the topic is about robustness, privacy, and attribution. Our first speaker would be Mr. Yash Kuzi from the University of Surrey, and he will present multiple watermark embedding for neural radiance fields. So please join me to welcome Mr. Yash.